Hey everyone, I am Miss Hu, your physics teacher. In this video, we're going to go through the concept of electrical resistance. I'll be covering specifically only the content which the students who are taking IGCSE Physics need to know in order to answer their examinations. Of course, there's a lot more to know about this topic, so please feel free to do your own research. What I'll be covering in this video are: what is resistance, Ohm's law, the relationship between resistance, current, and potential difference, the current voltage graphs for a resistor of constant resistance, a filament lamp, and a diode, as well as the factors affecting the resistance of a conductor. So first things first, let's go through what resistance is. Now, electrical resistance is the measure of how much a material or device opposes the flow of electric current. The unit of measurement of resistance is in ohm, and the short form for ohm is the Greek letter omega, as seen in this slide. So by the way, if you are a Trekkie nerd just like me, you'll get this joke. Yes, resistance is futile. But some will argue, no, resistance is voltage divided by current. Well, if you like TV shows like I do, you would find this meme very funny. Otherwise, just enjoy this meme. So anyway, for now, let's look at the relationship between resistance, current, and potential difference. You need to know that resistance is calculated as the potential difference, which I'll write as PD for short, divided by current. If we use symbols, this is more commonly written as R equals V over I, and more commonly written as V equals IR. So this is the formula you will need to know that relates resistance with current and potential difference. Now, of course, you need to know the corresponding units. Resistance, as we already know, is ohm. Potential difference, or PD for short, is measured in volts, while current is measured in amperes. The formula for resistance is actually derived from Ohm's law, which we'll look at shortly. But before we take a closer look at Ohm's law, let's first have a look at this comic, which actually visualizes very clearly and perfectly the difference between current, potential difference, and resistance. So ohm, as depicted over here, is actually the resistance. And as you can see, the resistance is what is providing an obstacle against current, which is ampere here, from flowing. Volt, which is actually voltage or potential difference, is providing the push to make current flow through this conductor. So as you can see, potential difference is actually pushing current to flow through this material, but resistance is providing some obstruction against current from flowing. Now let's take a look at Ohm's law. Ohm's law states that current flowing through a conductor is directly proportional to the potential difference applied across its ends, provided that temperature and other factors remain constant. So what is all this? Just think of it this way. There were many experiments that were conducted to investigate the different measurable quantities when it comes to electricity. So this physicist, George Ohm, discovered that there was a relationship between current and potential difference. So based on the many electrical circuit experiments that were conducted, graphs were drawn, and they found that current was directly proportional to potential difference. Because they got a linear relationship, in this case specifically directly proportional because it went through the origin, they came up with the concept of resistance, which was a measurable quantity to relate current and potential difference. Now, by the way, this relationship is only true for ohmic conductors. So how does this graph relate to the equation? So what we have here is a graph that shows current against potential difference. As we know, resistance is potential difference divided by current. I'm writing in short form here to make it a lot easier to comprehend. Now, how do we relate this formula to the graph? So if we look at the graph, we can calculate the gradient this way. I'm going to write here the gradient with the symbol m is calculated as a change in y over change in x. Now, what's on the y-axis? Current. So current goes on top, while potential difference is on the x-axis. So that goes at the bottom of the fraction. If you look at these two formulas, obviously they're not the same. So let's try to make them the same. In order to do that, what we can do with this equation is to inverse it. So we would get 1 over m equals to v over I. Now, as you can see, on the right side of both of these equations, these are exactly the same. So what this tells us is that the inverse of the gradient of the graph would give us the value of the resistance. You can also think of it as the gradient is equal to the inverse of the resistance, depending, of course, what you want to calculate. So on this graph, I've drawn two lines here because sometimes you may be asked to compare the resistance of two different materials depicted here in this graph. So what we have here are two graphs which are labeled here as A and B. So based on this relationship, we now know that the gradient is the inverse of the resistance. So this means that the greater the gradient, the lower the resistance. So therefore, the resistance of A is lower than that of resistance of B. And this is because the gradient of A is greater than the gradient of B. Now, if you can't really visualize this and you can't see how the gradient relates to the resistance, another way to figure this out is by looking at the graph. So this is one trick which I share with my students. So in order to figure out which graph is showing the higher value of resistance, you can draw a line like so. So from here you can see for the same value of the current, A has a lower value of potential difference compared to B. So if we know this formula, you can see that in order to get a higher value of resistance, given the same value of current, you need to have a higher potential difference. So with the same current value, B has a higher potential difference, which automatically means that B has higher resistance. So that also is another way to check which graph is showing us the higher value of the resistance. So that's another way you can determine which graph is showing us a higher value of resistance. So typically we see a current potential difference graph, but sometimes they may give you a potential difference current graph instead. That means that potential difference is on the y-axis this time, while current is on the x-axis. This is sometimes preferred because it's a lot easier to see the relationship between the gradient and resistance. Just to show you really quickly, we already know that resistance is calculated as the potential difference divided by current, R equals V over I. Now from the graph, we know that the gradient is a change in y over change in x. So we've got m as the symbol for gradient here. Remember, what's on the y-axis goes on top, and that's a potential difference. What's on the x-axis goes at the bottom, which is current. And as you can see from these two equations, the values on the right side of both equations are identical, which immediately tells us that the gradient is equal to the resistance. So this is much easier for us to be able to quickly analyze the graphs because the gradient value shows us the resistance. So a graph that has higher gradient automatically means it has higher resistance. So if we look at this diagram, let's say these two graphs represent two different materials. We just need to compare the gradient to compare the resistance. So let me just label now this as C and D. And because the gradient of C is greater than D, that means that the resistance of C is greater than the resistance of D. Again, this is because gradient of C is greater than the gradient of D. If you want to use the same method as I did earlier in order to check is this really true, let's now take this way. So with the same value of current, the graph that shows us the greater potential difference for that same value of current will automatically mean that it has greater resistance. And as you can see, C has higher potential difference compared to D for the same value of the current. And again, this proves that the resistance of C is greater than the resistance of D. So if you're given a graph that relates potential difference and current, do be careful. Always check what's on the y-axis and x-axis to make sure that you are analyzing them correctly. So just to backtrack, remember for a current potential difference graph, the gradient is the inverse of the resistance, while for a potential difference current graph, the gradient is equal to the resistance. So always check what's on the y and x-axis before you do your analysis. Now let's take a look at some other graphs. So again, for IGCSE, they focus more on current voltage graphs. That means current is on the y-axis while potential difference is on the x-axis. So the graph that we saw earlier was a linear graph that went through the origin, meaning that the relationship is directly proportional. This kind of graph is for ohmic resistors. So ohmic resistors quite simply mean resistors that obey Ohm's law. And if we recall, Ohm's law states that current is directly proportional to potential difference, provided that temperature and all other factors remain constant. So this is true for a lot of conductors and resistors. However, you do have to learn about other kinds of components as well. Now, for your information, not all conductors are ohmic conductors. Only a fraction of all conductors that can conduct electricity that exist are ohmic conductors. Many of them are actually non-ohmic. Non-ohmic conductors do not obey Ohm's law. So in your syllabus, you only need to recognize two graphic examples of non-ohmic conductors. The first one you need to be aware of is the graph for filament lamps. So filament lamps are the lamps which have a filament in them, which gets very hot, and the heat energy is then converted to light energy. They're not very efficient lamps, and in most places we don't use them anymore, but we still have to learn about them anyway. So this is the symbol for a filament lamp. Obviously, the lamp does not obey Ohm's law. If we look at the positive quadrant, you can see that the potential difference is increasing proportionally to current. So if we recall what we've learned about the relationship between resistance and the gradient of a current potential difference graph, the resistance is the inverse of the gradient. So you can see that in this graph, the gradient on the positive quadrant is decreasing before becoming constant. Because the gradient is decreasing, this means that the resistance is increasing, and it's increasing at an exponential rate. So as more current flows through the filament lamp, it's getting hotter, which means that the resistance of the filament is also increasing. The second graph which you need to recognize is the current potential difference graph for a diode. So if you haven't learned about diode, please watch my video on semiconductor diodes. For now, you just need to know that diodes are not actually conductors, they're semiconductors, and they're a component that allows current to flow in one direction only. That means that if you connect it the other way, current will not flow. So from this graph, you can see also that the diode does not obey Ohm's law. The current for the most part is zero until it reaches a minimum potential difference. Then you find that current will increase exponentially. You can think of it as, because this is a semiconductor, it has a certain amount of resistance, and the current needs to overcome that resistance with a certain amount of potential difference before finally the current can flow. And as you can see in the negative side, when it's connected the opposite way, there's no current, it's actually zero. So for your syllabus, you just need to recognize these three graphs and roughly how to sketch them, especially in the positive quadrant side. So remember that for resistors, which are ohmic conductors, it is a linear graph that goes through the origin. Filament lamps should show an increasing resistance. So for current potential difference graph, this means that the graph is decreasing in gradient, while for a diode graph, it will be zero at first and then starts to increase exponentially after a certain amount of potential difference. Now let's take a look at the factors which affect the resistance of a conductor. Just for your information, there are actually 4 factors which affect the resistance of a conductor, but for your syllabus, you only need to learn 2. So let's just focus on these 2 for this video. The 2 factors are length and cross-section area. Remember that every time we want to investigate factors, we only investigate one factor at a time. So which means that as we change one factor, all other factors should remain constant. Let's learn first about length. It's actually very logical. So let's say if this was a wire and we've got another wire with a much greater length like this. When comparing the lengths, we have to make sure that the cross-section area of both wires are identical. Now imagine that the electrons, which are essentially the electric current, are trying to flow through the wire. So if we have current flowing through the shorter wire and current flowing through the longer wire, just think, which one will have greater resistance for the current to overcome? Well, obviously the longer wire, because there's more material to overcome. So the greater the length, the greater the resistance. What you need to know is that the resistance of the conductor is directly proportional to the length. I'm going to write it this way: the resistance is directly proportional to the length. That means that if the length is doubled, the resistance is also doubled. if the length is tripled, the resistance is also tripled. There's a direct correlation between the resistance and the length. Now let's look at the second factor, which is the cross-section area. Again, it's very logical. Let's say we've got two wires, one with a smaller cross-section area and one with a much larger cross-section area. For fair comparison, once again, we have to make sure all other factors remain the same. So let's say both of these wires have identical lengths. So I want you to think, which wire would be easier for the electric current to flow through? The smaller cross-section area or the larger cross-section area? Well, yes, obviously, the larger cross-section area would be easier for the electric current to flow through. And that means that the larger cross-section area provides lesser resistance compared to the smaller cross-section area. So this means the greater the cross-section area, the lower the resistance. The relationship is an inverse relationship. The resistance is inversely proportional to the area. So this inverse relationship here means that if the area is doubled, the resistance is halved. So 2 becomes 1 over 2. If the area is tripled 3 times, the resistance becomes 1 over 3, 1/3. So it's an inverse relationship. You are required to know this relationship because sometimes you may be asked to calculate the value of the resistance of a new conductor with different lengths and cross-section areas. Now, one thing that you do have to take note of is that sometimes the question gives you a different value of diameter. And many students, when they see diameter, they make a mistake thinking that the diameter has a similar relationship with cross-section area, but it doesn't. Let me show you what I mean. So, cross-section of a wire is normally circular. And as you should know by now, the relationship between area and diameter can be calculated this way. The area that we're calculating is the area of a circle, which is pi r squared. But because the question gives us the value in diameter, we now need to compare the area against the diameter. We know that diameter is, of course, 2r, which means that r is d over 2. So what this means is that a is actually pi times d over 2 squared. And then in the end, you'll get pi d squared over 4. So you can see that the relationship between the area and diameter is not a directly proportional relationship. There is a squared value. So if you want to look at the relationship between resistance and diameter, again, I'll just draw this to help us with some visualization. So smaller cross-section area and larger cross-section area. Let's say these two wires have identical lengths. We know that resistance is inversely proportional to the area. However, because area is pi d squared over 4, this means that the relationship between resistance is actually proportional to d squared. In case you're wondering how this works, this is a mathematical thing. So I don't want to go through this in much detail, but just to show you very quickly, in case you want to know how to come up with that relationship, we can write R equals to K over A, because you got to remember that when you want to create an equation out of a relationship, you have to add a coefficient. So in this case, it is K. So given that R equals K over A, this is R, this means that R equals K divided by pi d squared over 4. Or you can think of it as R equals K divided by pi d squared over 4, which means that it is K times 4 divided by pi d squared. So you get 4k over pi d squared, and that would be R. So when you want to come up with a relationship like this, you would strip away all the constants, which in this case are 4k and pi, leaving you with d squared. That's how you get R is inversely proportional to d squared. So what this relationship tells us is that if d was doubled, 2 times more, 2 squared is 4. That means the resistance now becomes 1 over 4. If d was 3 times more, 3 squared is 9. So if d is 3 times more, the resistance would become 1 over 9 of the original. So do take note that when it comes to diameter, you have to remember that the relationship between area and diameter is squared. So that's why the relationship between resistance and the change in diameter is that the resistance is inversely proportional to diameter squared. If you'd like to see some examples of how this works, do check out my video where I have gone through some past year questions where we calculate the new value of resistance based on the changes in the different factors. And that is all for this video. So if you found this video to be educational and helpful, please click like and subscribe for more free physics lessons. Do check out my YouTube channel for videos on other topics which you might find helpful. If you'd like access to notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Do help me keep making free educational video lessons and lab practicals. Donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. Happy studying!